Hey everybody, and welcome back to Calc 3 Online. So in this video, it's going to be our third and final day with line integrals. And I'm basically going to start off by showing you sort of a third line integral. And it looks like this, okay? And it's really very related to another one. I'm actually also going to show you how mathematically it really is the same as another one. So I'm going to start off with that basically, and then the rest of this video will basically be spent doing some examples, because I really think we've been spending a lot of time on the theory of line integrals, but we really need to take some time and do a little bit with the actual computation of them, okay? So I'm going to start off, and I'm just going to define like some vector field as like PQ. Basically like a two-dimensional vector field. I'm just going to do everything here in 2D, but it's really just for my ease of writing. And if you wanted to, you could extend everything I'm about to talk about to higher dimensions as well. We also know that there's this unit tangent vector, which is r prime over the magnitude of r prime, which I could also write as basically 1 over the magnitude of r prime times the vector dx dt, and then dy dt, right? And so using these things, I can basically create this line integral, which is the line integral with respect to x and y together over some curve c, okay? So it kind of encapsulates, we talked about those line integrals where you would sort of project into just like x or project into y or something. This line integral takes into account both of those and kind of does them together. So I'm going to start with this line integral we saw before. So the one that's just f dot t ds, okay? And so if I do this f dotted with t, right? This part right here would just literally become p, and then I'm just trying to think about how I want to write all this. So we'll do dx dt over magnitude of r prime. I'm just going to write magnitude of r prime, right? So basically this first component times p, and then plus this one times q. So then plus q times dy dt over magnitude of r prime. And then if you remember, ds, right? ds is just magnitude of r prime dt, right? And so one thing I'm seeing here is I can cancel those things, right? Because really it's like all of that right there. So that's nice, okay? So that's one thing I can kind of do to simplify this problem a little bit. So now I have p dx dt plus q dy dt, and then all of that is times dt. And you might be seeing where this is going. Basically just get rid of the dt's, and you'll have integral p dx plus q dy. And, p could be a function of x and y, q could be a function of x and y, but those two things are really the same thing right there. So, so this right here is just built off of that. And so actually, to build off of those things, we have that integral of f dot dr, this weird notation, right, that we talked about in the last video, is really just the same thing as this. So if this, right, is equal to this kind of format, and this is now the 3D one, right, then by like transitivity, we would also have that the integral of f dot dr is the same as that. So now at this point, we have kind of built up all the different ways that you can write line integrals. Some of the most important takeaways that I just kind of wanted to sum up here. So this integral of c f dot dr really is equal to this, which is really equal to this kind of structure. I'm just going to say dot, 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 because you could keep going, right? All of those ones, basically, there is, it is, I'm going to just say it's dependent on direction. Okay, so the direction of that curve C, right? That curve C is going to dictate the sign sort of your answer, right? The other kind of line integral where we just go and just do like an integral over some curve of, so integral over curve C of like f of x, y, ds. This one where this is really with respect to arc length. For this one, we like just parameterize the thing. We go like, A to B or something, and we have like maybe f, we could just say like of r of t, and then we have this magnitude r prime dt, like that's my ds, right? This one does not depend on direction, okay? You're going to get the same answer whether you go one way along the curve or backwards along the curve. Does not matter, okay? So this is kind of all the different ways that we do line integrals. What you want to think about with this new one that I just sort of showed you, when we do a dot product, you're thinking of this with a vector field, right? So you're thinking of how much does all these little like micro dot products add up together in the x direction, the y direction, the z direction, or however many spatial dimensions you have, and then you sum it all up with the integral. That's what you can just kind of encapsulate into this dot product right here. And because it's built on dot products, there's like a directional component, and the vector field can definitely affect the overall value of it. Here we just literally are concerned with how much stuff is above or below the curve in space, right? So this is much more similar to the kind of integral that you're used to in Calc 1. This is a little bit different. This is more of, still consider a line integral, but you're more looking at the connection between a vector field and the little tangent vectors, basically, on the curve. Okay, so I want to go through just kind of two computations with these. Okay, and actually, the one that I want to do is, so you're going to see some written like this, where you get this line integral, something dx, something dy, and we haven't seen any of those yet because I haven't given you that notation until today. So I want to evaluate this, okay, and curve C, like that you're integrating over, is built out of three parts, okay. C1 is the line segment from -5, -3 to 0, 2, and B is all right, so C2 is the arc, this parabola, and then, so it's just those two. Sorry, my brain wasn't doing well there for a second. So for these kind of problems, you still will need to parameterize everything here. And so when you do one of these, let's take like curve 1 right here. So we know that like a line in vector form, so this is curve 1, looks something like xy, right? And then you got to pick a point that it goes through. So it goes through -5, -3, and then plus t times like a direction vector, right? And so you can see that you go up 5 and you go over 5 between these points. So the direction vector can just be 5, 5. So this is saying that like x equals -5 plus 5t, and y is -3 plus 5t. So when you do one of these line integrals over a curve like this, the general idea is, and I wish I'd sort of done this at the top, but This line integral right here can basically be thought of as the line integral over curve 1 with y squared dx plus x dy, and then plus the line integral over curve 2, right? Y squared dx plus x dy. And that's just because integrals are additive things. So you can do it over this chunk and then just add it to this chunk. So we're sort of setting up that part right now. I've got x and y, and the only thing I kind of don't know is the bounds, right? Like if I start at t equals 0, right? T equals 0 would, in this parameterized line, it would give me the -5, -3. And to get to this point, t would just be 1, right? Because if I do -5 plus 5, I get 0, and then -3 plus 5 is 2, right? So for my first kind of part here, I'm going 0 to 1, and then y is -3 plus 5t, so y squared, and then I have, I might as well put this up here. So I need dx and I need dy, and so I need to take like the derivatives of these things. So dx is just going to be 5 dt, and then dy would be also 5 dt, right? Just go and plug in dx right here. And so dx is 5 dt, and then it's like plus x, which is -5 plus 5t, and then dy is also 5 dt. All right, so now that we've got everything in terms of like dt, we can also take, there's a 5, right, in these things. We could pull a 5 out if we wanted. And then we basically can just combine everything. So we've got we're just going to square out that first thing. We get 25t squared, and then we get minus 30t, and then plus 9. And then we have a plus 5t minus 5. So I'm basically just combining like terms. And you can just take this dt out. So then it's just honestly, at this point, it's like a nice just polynomial thing that, don't forget about the 5 that's in here, and that comes out of the derivative. If you do all that out, you should just get -5 over 6, okay? So that's like half the problem. That's like doing this part. And now we're going to do this curve, okay? So now we're going to parameterize that parabola. And so if you ever have a function that is defined in terms of just one variable, you can do this kind of trick where you're like, I'm going to let y equals y and x then just equal 4 minus y squared. You can switch it to t if you want to, but you can also just do a normal old, you'll do like a dy integral basically here. And so I would just do it this way, and then I'm going to go and plug everything in on this second curve. So I'm basically doing this part right here. So y squared is now just literally y squared, right? And also here, I guess we need dx, right? Dx is going to be just minus 2y dy, right? So I'm going to pop that in. Minus 2y dy is my dx, right? X is right here, and then dy is just going to be dy, right? So then I have plus 4 minus y squared dy, right? And the nice thing about doing it this way is now you can just look on the green curve, you go from -3 in the y to 2 in the y. So you're really just doing a normal old integral that you're kind of used to from Calc 1. Same kind of trick as above. I'm basically going to just combine like terms. So I've got -3, 2, I have negative 2y cubed, and then I have plus 4 minus y squared dy. Again, a nice polynomial integral. I'm not going to like go through all the solving of that. This becomes 40 and 5/6. And so if you do this plus this, which would be my final answer, this whole thing, right, is what I'm just talking about. That, if you do those two, add them together, you would just get 40, right? Just kill off the 5/6 part. So that's it. So that's how we do these kind of weird dx, dy kind of line integrals. And I want to just do one more. So we basically, in this one, do all the same sort of stuff that we just did before, but it's just more good examples. So I'm going to do curve 1 in blue, do curve 2, or sorry, I guess it's curve 2 in blue, curve 1 in green. So curve 1 is just y equals x squared. So for this one, I'm just going to let, maybe here I will do it kind of a different way. So here I'm going to let x equals t. Like before, I kind of did just let y equals y. But just to show you, you can do it this way too. I'm going to let x equals t, right? And then y equals t squared. And then, so it's going to be just another way to do it. And I'll just basically convert everything to t. And so if I have that definition for x and y, dx is dt, and dy is 2t dt, right? So now I can go and plug everything in for curve 1. X squared plus y squared is t squared plus t to the 4th, right? And then I have dx, which is dt, minus 2 times x, which is t, times y, which is 2t d. Nope, I'm using the wrong part there. X is t, y is t squared, and then dy is 2t dt. And then you just need to think about this directional piece right here. So we know that at t equals 0, right, we're at 0, 0. So that's my starting spot. And then I need to go up to where x squared meets square root of x. And so that would be 1, right? And so, x equals 1, right, would do it, because then y equals 1 also. So t goes from 0 to 1 in this problem. So then combine all your like terms. You can take that dt out. So we got like t squared plus t to the 4th. Minus 2, no, there's a 4 in there, minus 4 t to the 4th, I think I did all that and didn't miss anything, dt, right? And so if you do that out, again, a very nice polynomial integral, you get negative 4 over 15. So that's curve 1. Curve 2, I'm going to do something very similar. I'm going to let x equals t, right? And then I'm going to let y equals square root of t. And so dx is dt, and y is 1 over 2 square root of t dt. Right? So here, notice the directional piece right there, right? It's saying that we're going this way, whereas before we went that way, right? And so this is a good example to show you where that directional piece really can change some stuff. So if I go and plug it in, the initial stuff is fairly straightforward. I have just t squared, x squared, x is t, y squared is square, you're squaring the square root of t, so you just get t. Dx is dt, minus 2 times x times y, and then dy. Okay, but this is the kind of important part I want you to see. So we start up here, right? and we end down here. So I need to end at 0 this time, end at 0, and start at 1. So this is kind of where you can see that these things have like a directional component to them, right? If I start at 1, t equals 1, I'm up here at x equals 1 and y equals 1, and then I end at 0, 0. So you do need it that direction. That is important, right? So I'm going 1, 0. We got t squared plus t. This and this would cancel. This and this would cancel. So I really would just have minus t dt. So really those even cancel. And then you get a nice integral there again. That's negative a third. And so if you put it together, the line integral here of x squared plus y squared dx minus 2xy dy is just going to equal the line integral over curve 1 plus the line integral over curve 2. And obviously you should have things in here, but I'm being lazy because I don't have room. And that would equal negative 4 over 15 minus 1/3, which is equal to negative 3 over 5. There you go. So that is it. So between this video and the last few on line integrals, you have seen examples of every kind of line integral at this point. So hopefully we feel okay with this. The theory, I think, in these is way harder than the computation a lot of times. Most of the theory is a little out there, but once you kind of get your hand around what you're doing, computationally, fairly straightforward. Parameterize it, which can be the hard part, and then go and plug in everything from there, and then you typically end up with nice integrals to solve.